Hi everyone, welcome back to my channel, Solve It with Arash. Today we are going to focus on Vieta's formulas for quadratic equations, a quick way to connect the roots of a quadratic equation to its coefficients without solving the quadratic. It is a very useful tool for solving problems with quadratics. Before we start, if you enjoy math content and you'd like to see more, please like and subscribe. Now, with no further ado, let's jump in and solve some problems. Okay, here's the question. Determine the sum and product of the roots for each of the following quadratic equations. The first equation, x squared minus 2x minus 3 equals 0. This is a quadratic where the leading coefficient is 1, the linear coefficient is -2, and the constant term is -3. And it is given in the standard form. It means all the terms are on one side of the equation and the other side is just 0. To solve this quadratic, you can try factorizing the quadratic, write it in factored form, or you can use the quadratic formula. In this case, I'm going to use the factorization of the quadratic. This quadratic can be factored into x minus 3 times x plus 1 equals 0. Therefore, the roots of this quadratic are x equals 3 and x equals -1. Now that we have the roots, let's draw the graph of this quadratic just for fun. I'm going to find the x-intercepts on the x-axis, one at -1, the other one is at 3. Since the leading coefficient is positive, then the parabola will open upward. Then I can connect these 2 points with a smooth line. I'm trying my best. And this is how the graph looks like. Now, we want to find the sum and product of the roots. Now that we know the roots, I can easily calculate the sum, which is going to be 3 plus -1, that equals 2, and the product equals 3 times -1, which equals -3. Now, if I compare these two values with the coefficients of the quadratic, let's see what we can find. I can see a -2 as the linear coefficient of the quadratic, and -3 is the constant term. So it seems like the linear coefficients is the negation of the sum of the roots, while the constant term equals to the product of the roots. This is the case when the leading coefficient is 1. Now let's try the second example where the leading coefficient is not 1. Here is the second equation. 2x squared plus 9x minus 5 equals 0. In this quadratic, the leading coefficient is 2. The linear coefficient is 9, and the constant term is -5. And the quadratic is given in the standard form. First step, we factorize the equation. This equation in factor form is 2x minus 1 times x plus 5 equals 0. Therefore, the roots of this quadratic are x equals 1 over 2 and x equals -5. Again, let's draw the graph just for fun. One x-intercept is at -5, and the other one is at 1/2. The leading coefficient is positive, so the parabola opens upward again. Okay, not too bad. Now, since we're looking for the sum and product of the roots, and we have the roots, we can easily calculate them. The sum of the roots is going to be 1/2 plus -5. By finding the common denominator and adding these two numbers, the result is going to be -9/2. Product of the roots is 1/2 times -5, which equals -5/2. Now let's compare these two values with the coefficients of the quadratic equation. For the sum of the roots, the answer is -9/2. In the previous example, we noticed that the sum of the roots was the negation of the linear coefficient. Let's see if it works here as well. It seems no. The linear coefficient is 9. The negation of it is -9, but here we have -9/2. But wait a second. 2 in the denominator. Maybe that's the 2, which is the leading coefficient. That's a good assumption. What about the product of the roots? The answer is -5/2, while the constant term is -5. It seems that the denominator is coming from the leading coefficient again. So we can make an assumption now and then try to prove it. The assumption is the sum of the roots in a quadratic is equal to the negation of the linear coefficient divided by the leading coefficient, and the product of the roots is the constant term divided by the leading coefficient. Okay, here's the third and last quadratic. ax squared plus bx plus c equals 0. So the goal is to find sum and product in terms of a, b, and c. Let's assume the roots of this quadratic are called r and s. Then the factored form of this quadratic is a times x minus r times x minus s equals 0. The expanded form of this equation is ax squared minus a times r plus s times x plus ars equals 0. To calculate the sum of the roots, I can divide the linear coefficient in the expanded form by -a. The result is r plus s. To calculate the product of the roots, I can divide the constant term ars by a. The result is rs, which is the product of the roots. So to calculate the sum of the roots, I technically divide the linear coefficient, which is called b in the main equation, by -a. To calculate the product of the roots, I divide the constant term, which is called c in the main equation, by a. These two equations, or these two formulas, are called Vieta's formulas for quadratics. And that helps us to find the sum and product of the roots of the quadratic without calculating the roots. As an example, we can try it on the second example, which was 2x squared plus 9x minus 5 equals 0. In the first solution, we solved it, we found the roots, and then we calculated sum and product. But now, without finding the roots, we can find the sum and product. where sum is going to be the linear coefficient over 2, the negation of that, which is going to be negative 9 over 2, and the product is the constant term over the leading coefficient. We found the same answers with the first solution, but now we can find the answer faster with one step less than before. And it's going to be very useful when the quadratic is not factorable and it takes time to calculate the answers using the quadratic formula. While you just need the sum and product of the roots, you can just try that, b over negative a and c over a respectively. That's everything that we need for now about Vieta's formulas for quadratics. I hope you enjoyed this lesson, and I'll see you next time.